Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 2085, count common words with one occurrence. In this problem, we'll explore how to identify words that appear exactly once in two separate arrays. We'll break down the problem, analyze different approaches, and implement an efficient solution. Let's dive in. In this problem, you are given two arrays of strings, words 1 and words 2. The goal is to determine how many strings appear exactly once in each of the two arrays. A string is considered a common word if it meets this condition. It must occur only once in words 1 and only once in words 2. The output of the problem is an integer, which represents the total count of such common words. For example, the input might consist of two lists of strings, and you need to apply the given condition to identify qualifying words and calculate the result. In the first example, words 1 contains the strings, LeetCode, is, amazing, as, is, and words 2 contains, amazing, LeetCode, is. The output here is 2. This is because LeetCode appears once in both arrays, and amazing also appears once in both arrays. However, is appears twice in words 1, so it does not satisfy the condition. Additionally, as appears only in words 1 and not in words 2, so it is also excluded. As a result, the two common words are LeetCode and amazing, giving us the output 2. In contrast, for the second example, words 1 contains B, BB, BBB, and words 2 contains AA, AAA. Here, there are no shared words between the two arrays, so the output is 0. In another example, words 1 is UB, and words 2 is UB. The output here is 1. Let's analyze why. The word appears once in words 1 but 3 times in words 2, so it does not meet the criteria. However, the word appears exactly once in both arrays, meaning it satisfies the condition of being a common word with one occurrence. Therefore, the result is 1. These examples showcase how the problem focuses on identifying strings that appear exactly once in both arrays, while excluding strings that appear multiple times or are not shared at all. This problem also comes with a few constraints. The lengths of words 1 and words 2 can range from 1 to 1000, and each string within these arrays can have a length of up to 30 characters. All strings consist solely of lowercase English letters. There are some edge cases to consider as well. If the two arrays do not share any common strings, the output should be 0. Similarly, if all strings in one array appear more than once, the result should also be 0. Even arrays containing only one word can produce a valid count if the condition is met. Additionally, the solution must handle words of varying lengths correctly, whether they are single letters or longer strings. To solve the problem of counting common words with exactly one occurrence, we explored a few different approaches. First, the brute force approach. The idea here is straightforward. For each word in the first list, we count how many times it appears in both lists. If the count is exactly 1 in each list, we increase our result count. This method uses nested loops, where the outer loop checks each word, and the inner loop counts its occurrences. However, this approach has a high time complexity, n*m in the worst case, where n and m are the sizes of the two word lists. While it works for small inputs, it quickly becomes inefficient as the input size grows. The drawback lies in its repetitive counting process, making it impractical for larger datasets. A more efficient solution involves using hash maps to optimize the process. Instead of counting occurrences repeatedly, we pre-compute the frequency of each word in both lists. With two hash maps, one for each word list, we store the frequency of every word. Then, by iterating through the keys of one hash map, we check if each word appears exactly once in both hash maps. This eliminates the need for nested loops. The time complexity for building the hash maps is n plus m, where n and m are the sizes of the two lists, and checking the common words adds another min, n, m step. Overall, this approach is much faster, with a total time complexity of n plus m. It does require additional space for the hash maps, but the trade-off is worth it for the efficiency it provides, especially with larger datasets. We also considered some alternative approaches. One idea was to use set intersection, where we find the common words between the two lists using sets and then filter for words that appear exactly once. However, this method has a drawback. Converting arrays to sets removes frequency information, meaning we would still need additional processing to count occurrences. Another approach was the two-pointer technique, which works if both word lists are sorted. With this method, we can traverse both lists simultaneously to find common words while applying the frequency constraint. However, the sorting step adds a complexity of O, n log n plus m log m, making it less efficient compared to the hash map solution. While both alternatives have their merits, they are either less efficient or more cumbersome to implement. Comparing these approaches, the brute force method is simple but inefficient for larger inputs due to its O, n*m, time complexity. The hash map approach is highly efficient, with a time complexity of O, n plus m, but it does require additional space to store the hash maps. The set intersection method is less practical because it loses frequency data, and reprocessing adds unnecessary overhead. Lastly, the two-pointer technique is only viable if the input lists are sorted, and the sorting step introduces additional complexity. Overall, the hash map-based solution strikes the best balance between efficiency, simplicity, and scalability. By avoiding repetitive counting and leveraging pre-computed frequencies, it provides an elegant and optimal way to solve the problem. To solve the problem of counting common words that appear exactly once in two lists, we need a structured approach. First, we need to understand the input and output. The input consists of two lists of strings, words 1 and words 2, where words can appear multiple times. Our output will be a single integer that represents the count of words that occur exactly once in both lists. Next, we need to choose the right data structure. Using Python's collections counter is ideal because it provides a hash map where the keys are words and the values are their frequencies. This allows us to efficiently count occurrences with an average time complexity of O(1) for both lookups and updates. Once we have the data structure, we use counter to compute word frequencies in both words 1 and words 2. This can be done with just a few lines of code, creating count 1 and count 2, which store the frequency of each word in their respective lists. Now that we have the word frequencies stored in count 1 and count 2, the next step is to filter for words that appear exactly once in each list. To do this, we iterate over the items in count 1 and count 2, selecting only those words where the frequency equals 1. These words are stored in two sets, unique_words 1 and unique_words 2. Sets are particularly useful here because they allow us to focus on unique words while enabling efficient operations like intersections. Once we have these sets, we compute their intersection to identify the words that are unique to both words 1 and words 2. Using the AND operator, we can directly find the common elements between unique_words 1 and unique_words 2. This approach ensures that we only consider words that meet the condition of appearing exactly once in both lists. The result of the intersection is a set called common_unique_words, which contains all the words that are unique to both lists. To calculate the final answer, we simply find the size of this set using the len function. This gives us the count of words that appear exactly once in both words 1 and words 2. Finally, we return this result as the output of our function. Let's recap some key insights about the algorithm. Using counter is essential because it allows us to efficiently count word frequencies without resorting to nested loops, significantly optimizing performance. Sets, on the other hand, make it easy to filter and find intersections, which are critical for solving this problem. We also handle edge cases effectively. For example, if either list is empty or if no word occurs exactly once in either list, the result is simply 0. This ensures that the solution is robust and handles all input scenarios gracefully. The algorithm relies on two main data structures, counter for fast frequency counting and sets for storing unique words and computing intersections. Let's walk through the time and space complexity. For time complexity, counting frequencies in both lists takes O, n plus m, where n and m are the lengths of words 1 and words 2. Filtering unique words also takes O, n plus m, and the set intersection operation is O, min, len, set 1, len, set 2. Overall, the total time complexity is O, n plus m. For space complexity, we need to store the frequency counts in unique words, which also requires O, n plus m, space. This means the algorithm is efficient and scales well with the size of the input. To put it all together, here's the final optimized implementation. We use counter to count frequencies, sets to filter and store unique words, and a simple set operation to compute the result. In the final steps of the implementation, we filter unique_words2 using the same logic we applied to unique_words1. Then, we compute the intersection of unique_words1 and unique_words2 to find the common words that meet the condition of appearing exactly once in both lists. Finally, we return the size of this intersection as the result. This solution is optimal for the problem constraints and handles edge cases efficiently. By leveraging the power of Python's built-in data structures like counter and sets, we achieve both clarity and performance in our code. This approach ensures that the solution is not only correct but also easy to understand and maintain, making it a great choice for solving this type of problem. This Python implementation solves LeetCode problem number 2085, count common words with one occurrence, using an efficient approach. The problem requires determining how many words appear exactly once in both input lists, words1 and words2. First, the collections counter class is imported to efficiently count word occurrences in both lists. The countWords method is defined, taking words1 and words2 as input. Within the method, counter is used to create two dictionaries, count1 and count2, which store the frequency of each word in words1 and words2, respectively. This step ensures that all counts are computed in O, n plus m, where n and m are the lengths of words1 and words2. Next, a variable common_count is initialized to 0. This variable will keep track of the number of words that meet the criteria of appearing exactly once in both lists. A loop iterates over the words in count1. For each word, the algorithm checks if it appears exactly once in count1, using count1, word, = 1, and also checks if it appears exactly once in count2, using count2.get, word, 0, = 1. The get method ensures that missing words in count2 default to 0, avoiding potential key errors. If both conditions are met, the common_count is incremented by 1. Finally, the method returns common_count, which represents the total number of words that satisfy the criteria. This approach has a time complexity of O, n plus m, due to the linear traversal of input lists and counters, making it optimal for large inputs. Here, we're implementing a method to count words that appear exactly once in two given arrays. First, we import the necessary utilities and define our class and method, countWords. The goal is to determine how many words occur only once in both arrays. To achieve this, we use two hash maps, count1 and count2, to store the frequency of each word in words1 and words2, respectively. The for loops populate these maps, or we use the getOrDefault method to handle cases where the word isn't already in the map, initializing its count to 0 before incrementing. This efficiently tracks the frequency of each word in both arrays. After populating the maps, we initialize a variable, commonCount, to keep track of the number of words that meet our condition. Now, we iterate through the key set of count1, checking each word's frequency in both maps. If a word appears exactly once in count1, and its frequency is also exactly 1 in count2, we increment the commonCount variable. This ensures that only words with a frequency of 1 in both arrays are counted. Finally, we return the value of commonCount, which represents the total number of words meeting the criteria. This implementation efficiently handles the problem by leveraging hash maps to track frequencies, ensuring a clear and concise solution. In this first example, we start by examining two lists of words, words1 and words2. The goal is to count how many words appear exactly once in both lists. To achieve this, we use Python's counter from the collections module to compute the frequency of each word in both lists. For words1, we get count1 as apple, 2, banana, 1, dog, 1, and for words2, we get count2 as banana, 1, dog, 1, cat, 1. Next, we initialize a variable common_count to 0. This will be used to keep track of the number of words that meet the criteria of appearing exactly once in both lists. We then iterate through each word in count1. For the first word, apple, it appears twice in words1 and does not appear in words2, so it is not a valid match. However, for banana, it appears exactly once in both lists, so it is valid, and we increment common_count by 1. Continuing with the iteration, the next word is dog. It also appears exactly once in both lists, so we increment common_count again, bringing its value to 2. At this point, we have finished iterating through count1, and the final value of common_count is 2. This means there are two words, banana and dog, that meet the criteria of appearing exactly once in both lists. The output for this example is common_count equals 2. Now, in the second example, we look at two completely disjoint lists, words 1 and words 2, where there are no common words at all. For words 1, the frequencies are car, 1, bike, 1, and for words 2, the frequencies are train, 1, plane, 1. After calculating the word counts for these lists, we again initialize common_count to 0. As we iterate through the words in count 1, we first encounter car. It appears exactly once in words 1, but it does not exist in words 2, so it is not a valid match. Similarly, the next word, bike, also appears exactly once in words 1, but not in words 2, making it invalid as well. Since none of the words in count 1 meet the criteria, the value of common_count remains 0. The final result for this example is therefore common_count equals 0, indicating no common words with exactly one occurrence. In the third example, we examine the case where both lists are identical and contain the words hello and world. Here, since both lists are identical, the word frequencies for words 1 and words 2 are the same, hello 1, world 1. After initializing common_count to 0, we iterate through the words in count 1. The first word is hello, which appears exactly once in both lists, so it is valid, and we increment common_count by 1. Next, for world, it also appears exactly once in both lists, making it valid as well. We increment common_count again, bringing its value to 2. At the end of the iteration, the final value of common_count is 2. This means both words, hello and world, appear exactly once in both lists, and the output for this example is common_count equals 2. This demonstrates how the solution works efficiently for identical lists. The key insight in this solution is the use of counter to efficiently calculate word frequencies, which allows us to quickly compare the counts of words in both lists. By focusing only on words that appear exactly once in both lists, we achieve the desired result with minimal computation. The time complexity of this approach is O, n plus m, where n and m are the lengths of words 1 and words 2, respectively. This is because counting words and iterating through the resulting dictionary are linear operations. The solution also handles edge cases effectively, such as when one or both lists are empty, when there are no common words, or when the lists are identical. This makes the approach robust and suitable for a wide range of input scenarios. To analyze the time complexity of our solution, we can break it down into two main steps. First, we use the counter class to count word occurrences in both words 1 and words 2. This requires iterating through each list a single time. If the lengths of words 1 and words 2 are m and n, respectively, then constructing count 1 and count 2 takes o, m, and o, n time. Next, we iterate through the unique words in count 1. If there are u unique words in words 1, this loop runs u times. For each word, we perform two constant time operations, checking if its count is exactly 1 in count 1, and retrieving its count from count 2. Together, the cost of this loop is proportional to the number of unique words, which is o, u. In the worst case, u equals m if all words in words 1 are unique. The overall time complexity is derived by combining the steps we just analyzed. Counting word occurrences in words 1 and words 2 takes o, m, and o, n, and iterating through the unique words in count 1 costs o, u. Since u is at most m, the total time complexity simplifies to o, m plus n. Now, let's consider the space complexity. The main contributors to space usage are the count 1 and count 2 hash tables, which store the frequencies of unique words from words 1 and words 2. If there are u1 and u2 unique words in words 1 and words 2, the space required for these counters is o, u1, and o, u2. Additional variables, such as the integer common_count and the loop variable word, only require constant space. Therefore, the overall space complexity is dominated by the counters, resulting in o, u1 plus u2. In the worst case, where all words are unique, this becomes o, m plus n. When comparing this solution with a brute force approach, the benefits of the optimized method become clear. A naive solution would involve nested loops to manually count the occurrences of each word in words 1 and words 2. This would result in a time complexity of o, m asterisk n, which is far less efficient than our optimized o, m plus n approach. The optimized solution uses hash tables to count occurrences in linear time, avoiding the need for nested loops. Now, let's evaluate the best, average, and worst case scenarios. In the best case, if both words 1 and words 2 are empty, the time complexity is O(1), since there's no data to process. On average, the solution runs in O(m plus n), proportional to the lengths of the input lists. Even in the worst case, where all words in words 1 and words 2 are unique, the solution still processes each word exactly once, maintaining the O(m plus n) time complexity. We can further justify the time complexity mathematically. Constructing the counter objects involves a single pass through each input list, which takes O, M, and O, N. Iterating through the unique words in count 1 costs time proportional to the number of unique words, which is at most M. For each of these words, retrieving the count from count 2 is a hash table lookup, which takes constant time. Combining these observations, the total time complexity is O, M plus N. Similarly, the space complexity is determined by the memory usage of the count 1 and count 2 hash tables, which require space proportional to the unique words in words 1 and words 2. Therefore, the overall space complexity is also O(m plus n). When working on this problem, there are several common pitfalls to watch out for. First, one of the most frequent mistakes is not accounting for exact occurrences of words. For example, if a word shows up more than once in either words 1 or words 2, it shouldn't be part of the final count. This often happens when coders fail to explicitly check the frequency condition. Another issue arises with case sensitivity. Since Python dictionaries treat word and word as distinct, overlooking this can lead to incorrect results. Normalizing the case by converting everything to lowercase can prevent this. Efficiency is another common challenge. Using nested loops to compare all words directly is highly inefficient, especially for large inputs, and can result in time limit exceeded errors. Instead, leveraging frequency hashing is a much more optimal solution. Additionally, edge cases like empty input lists are sometimes ignored. For instance, if words 1 or words 2 is empty, the function should gracefully handle this without runtime errors. Finally, some coders overcomplicate the logic by using unnecessary data structures like sets alongside dictionaries. However, a single dictionary per list is sufficient for solving this problem effectively. This problem teaches several important lessons that are particularly valuable in the context of coding interviews. First, it emphasizes the significance of pattern recognition, specifically, frequency counting. This is a recurring theme in array and string problems, so mastering it can help you tackle a wide range of related challenges. Another key takeaway is understanding the optimal spacetime trade-off. The best solution for this problem achieves O(n plus m) time and space complexity, where n and m are the lengths of the two lists. Being able to explain why this is efficient is a great way to showcase your problem-solving skills. Discussing edge cases is also critical during interviews. For example, demonstrating awareness of scenarios like empty lists, duplicate entries, or mixed case words can make you stand out as a thoughtful and thorough candidate. Additionally, this problem is connected to other LeetCode challenges. For instance, problem number 819, most common word, involves frequency counting with added constraints, while number 884, uncommon words from 2 sentences, focuses on finding words unique to one list. Problems like number 451, sort characters by frequency, and number 49, group anagrams, further highlight the versatility of hashing and frequency-based approaches. Exploring these related problems can deepen your understanding and make you more prepared for similar tasks. There are a few different strategies you can use to solve this problem, each with its own trade-offs. One straightforward approach is to use 2 hash maps, or dictionaries, one for words 1 and another for words 2. You can store the frequency counts in these dictionaries and then iterate through one of them to check if a word appears in the other dictionary with a frequency of exactly 1. This method is both efficient and easy to understand. Another option is to use a single pass with a combined dictionary. Here, you merge both lists into one and use a single dictionary to count frequencies. Then, you filter for words with a total frequency of 2, indicating they appear exactly once in each list. While this approach is concise, it can be harder to explain during interviews due to its less intuitive logic. Finally, there's a sorting-based solution. By sorting both lists, you can count occurrences using a 2-pointer technique. While this reduces space usage, the time complexity increases to O(n log n plus m log m), making it less efficient than the hashing-based methods. Each approach has its strengths, and the best choice often depends on the specific constraints and requirements of the task or interview setting. Great job following along. To summarize, we solved LeetCode problem number 2085 using a hash map to track word occurrences and identify common words appearing exactly once. We discussed the time and space complexities and highlighted key takeaways, such as the importance of hash maps for frequency-based problems. Thanks for watching, and we encourage you to practice similar problems to reinforce these concepts. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!